Every discovery begins with a new way of seeing. NASA's Nancy Grace Roman Space Telescope will reveal the universe on an unprecedented scale. With its powerful, wide-eyed view, Roman will map vast regions of the cosmos, seek the hidden influence of dark matter, and uncover the mysterious force driving the universe's expansion. With a wider view comes a deeper understanding.
So tonight on Space Oddities, we are doing a deep dive into the Nancy Grace Roman Space Telescope, which is due for launch on August the 30th. So we hope you stay with us for that, because we've got a lot of stuff to tell you about the telescope. This is a special edition. Our regular features, or most of them, will be postponed until next week. So I think we'll start with the most obvious question. Who was Nancy Grace Roman? And Daz is going to tell us all about why the telescope was named after Nancy Grace Roman. Take it away, Daz.
Won't be a second. I'm just... I've all of a sudden gone very bright. Right. Okay, then. Here we go. Right. As we know, very soon... that's strange. I haven't got my... Let me just come over here. Sorry, I do apologise for this. Something seems to have gone wrong. Won't be a second. Right. Right, so basically, we all know Nancy Grace Roman as basically the mother of Hubble. It was her tenacity and her determination for space telescopes to become a thing, and also to make sure that the Hubble actually flew. Basically, it says, from a bold idea conceived before the space age to one of humanity's greatest scientific instruments, the Hubble Space Telescope, excuse me, represents decades of visions, perseverance, and ingenuity. This is the story how we put an observatory into orbit and changed our understanding of the universe forever. Nancy Grace Roman, basically 1925 to 2018. It was not quite recently, really, when you think about it, that she passed away. Was a pioneering American astronomer and the first female executive at NASA, where she served as the agency's chief of astronomy during the 1960s and the 1970s. Her fundamental contributions to stellar classification and stellar motions, as well as her private role in developing space astronomy program, earned her the title of the Mother of Hubble. In May 2020, NASA Administrator Jim Bridenstine announced that the Wide Field Infrared Survey Telescope, a space telescope, would be named the Nancy Grace Roman Space Telescope in recognition of her enduring contributions to astronomy. Nancy Grace Roman's early life. She was born in 1925 in Nashville, Tennessee. Nancy exhibited an early passion for astronomy, forming an astronomy club at the age of 11. Despite facing skepticism from her peers and educators, she pursued her interests through her education at Swarthmore College and the University of Chicago, earning her PhD in 1949. Her research focused on stellar spectroscopy, leading to significant papers on stellar classification and motion. Roman's career began at the Naval Research Laboratory, where she advanced radio astronomy and laid the groundwork for NASA's space science initiatives. In 1959, she joined NASA as head of observational astronomy and later became its chief of astronomy. Her early efforts aimed to foster a community-driven approach to astronomy, bridging the gap between conventional ground-based astronomy and new space-based initiatives. One of her major achievements was overseeing the development of NASA's OAO, which was the Orbiting Astronomical Observatory program, which was a series of 4 satellites that launched between 1966 and 1972, two of which were successful. These missions included the OAO2 Stargazer and the OAO3 Copernicus, the direct ancestors of Hubble, Chandra, Swift, and many other astronomy satellites. Roman was also instrumental in the inception of the Space Telescope, advocating for its scientific potential and coordinating collaboration between NASA and the astronomical community. Her leadership helped secure funding and establish operational protocols for what was to come. Even after leaving NASA in 1979, Roman continued to contribute to science and education, advocating for women in the sciences and mentoring young students. She challenged gender norms and sought to inspire the next generation. Her recognition of her enduring impact, NASA named the Wide Field Infrared Survey Telescope in her honor in 2020. Roman's legacy remains significant, not only for her significant contributions, but also as a trailblazer for women in astronomy and leadership, roles in scientific research. She passed away on December the 25th, 2018, leaving behind a rich legacy in the field of astronomy and an inspiring example of for the future generations.
That's John Mather there, the Nobel Prize winning chief scientist for COBE in your picture, by the way.
Yeah, that's correct. I mean, she kept her finger in the pie, for all time. She didn't really give up on her dreams and following the advancements. So let's take a brief look at the development of space-based telescopes and Nancy Roman's important role at NASA. The fundamental problem: every ground-based telescope must peer through Earth's turbulent atmosphere, a churning sea of air that blurs, distorts, and absorbs light. For centuries, this was an unavoidable limitation. Astronomers could only wonder what the universe would look like more from above the skies. As I mentioned, the problem was threefold: atmospheric turbulence, pockets of air at different temperatures cause starlight to shimmer and blur, fundamentally limiting the resolution available by even the largest ground-based telescopes. Light absorption: Earth's atmosphere absorbs large portions of electromagnetic spectrum, including ultraviolet light and infrared light, entire wavelength ranges, and the secrets they carry were simply invisible from the ground. And also, finally, light pollution. Even in the most remote locations, human-made light and atmospheric scattering reduced contrast, obscuring faint, distant objects such as early galaxies and nebulae. As early as the 1920s, pioneer thinkers began to imagine a radical solution. German rocketeer Hermann Oberth speculated that telescopes could one day be launched into orbit aboard rockets. Others mused about the extraordinary possibilities offered by observatories placed on the surface of the moon, entirely free from atmospheric interference. In 1946, astrophysicist Lyman Spitzer published a landmark paper titled Astronomical Advantages of an Extraterrestrial Observatory. In it, he proposed constructing a large telescope in Earth orbit, one potentially featuring a mirror up to 50 feet in diameter that could observe the cosmos entirely free of atmospheric distortion. The audacity of his vision cannot be overstated. Not a single object had yet been launched into orbit, Rockets were still experimental, space travel a theoretical exercise. Yet Spitzer's paper ignited serious scientific interest from astronomers around the world and laid the intellectual foundation for everything that followed. For over a decade after Spitzer's papers, the astronomical community remained largely skeptical. Placing a telescope in orbit seemed fantastical, the domain of science fiction rather than science. Then, on the 4th of October 1957, the Soviet Union launched Sputnik, the world's first artificial satellite. A small metal sphere, barely the size of a beach ball, transformed the conversation overnight. If a satellite could orbit Earth, so could a telescope. Space age had begun, and with it, the prospect of the space-based observatory shifted from dream to plausible engineering challenge. NASA's first space telescopes through the 1960s, NASA pursued a series of small space-based telescopes under the Orbiting Astronomical Observatory program. These pioneering satellites demonstrated that observing from orbit was not only possible, but scientifically transformative. OA02 launched in 1968 and successfully observed ultraviolet light from stars and galaxies. Wavelengths completely blocked. Oh, sorry, something's happened there. Wavelengths that were completely blocked by our atmosphere. After the moon landings in the early 1970s, public enthusiasm and political will for expensive space programs waned considerably. NASA's budget was cut significantly, and the LST faced an uncertain future in competing priorities, crowded agenda. Many astronomers questioned whether the enormous cost of the Space Telescope was justified, where ground-based facilities could still deliver valuable science. Roman had to build a broad coalition of support across the astronomical community to make the case. Roman's persistence ultimately paid off. In 1977, the United States Congress approved funding for the project. After more than 3 decades since Spitzer's original paper, the Large Space Telescope was officially a reality, at least on paper. The path to orbit was marked by frustrating delays, technical complexity, and the launch past its target date in 1983. Of course, this is the Hubble we're on now. Then on the 28th of January 1986, the Space Shuttle Challenger broke apart 73 seconds after launch, killing all 7 crew. Members of the all 7 crew members. The grounding the shuttle fleet for over 2 years. Hubble sat in storage as engineers continued to refine its instruments, anxious to ascend their life's work skyward. The path to orbit was marked by frustrating delays. Technical complexity pushed the launch past its 1983 date. Then on the 28th of January 1986, the Space Shuttle Challenger broke apart 73 seconds, killing all the crew, which we have already said. And Hubble was also kept in storage all this time. After decades of advocacy, engineering, setbacks, and sacrifice, the Space Hubble telescope finally lifted off aboard the Space Shuttle Discovery on 24th of April 1990. It was deployed into an orbit approximately 547 kilometers above Earth's surface, well above the distorting atmosphere. Here you can see it being deployed actually from the Space Shuttle's payload bay. The mood at NASA was jubilant. Scientists who had devoted careers to this moment watched as their telescope climbed into the sky. Lyman Spitzer, then 73 years old, witnessed the launch of the observatory he had first imagined 44 years earlier. For a brief, glorious moment, everything seemed perfect. but it wasn't, was it? We all know the story of this. Shortly after launch, Hubble's primary mirror was found to have a spherical aberration due to manufacturing error, which initially caused blurring images. This was corrected in December 1983 during a servicing mission. The Space Shuttle Endeavour flew the servicing mission 1, which was STS-61, and involved installation of several instruments and other equipment over the days. Most importantly, the high-speed photometer was replaced with CoStar, a corrective optics package, restoring Hubble's full imaging capabilities. Hubble was saved. Basically, they gave it a pair of glasses. Hubble's precise measurements of Cepheid variable stars helped determine the universe is approximately 13.8 billion years old, resolving a decades-long scientific dispute. Observations of distant supernova contributed to the Nobel Prize-winning discovery that the universe expansion was accelerating, pointing to the existence of mysterious dark matter. Hubble's famous deep field images revealed thousands of galaxies in a patch of sky that appeared completely blank to ground-based telescopes, transforming our sense of the cosmos's scale. From tracking storms on Jupiter to absorbing Pluto's moons, Hubble was revolutionized our understanding of our own solar system as well as distant worlds. The Hubble Space Telescope is as much a human story as a scientific one. It spans a career of Lyman Spitzer, who first proposed it in 1946, championed it tirelessly, and lived to see it repaired and vindicated. It honors Nancy Grace Roman, who fought institutional resistance and bureaucratic inertia to secure its funding and development. Behind them stand thousands of engineers, programmers, and opticians, astronomers, and mission controllers, many of whom dedicated entire careers to a single instrument. Today, the Space Telescope Science Institute in Baltimore continues to operate Hubble with thousands of scientists and support staff, ensuring it's remaining one of astronomy's most productive tools. More than 3 decades after its launch, it remains operational. Its orbit is still stable and is expected to last into the 2030s. Each year, hundreds of scientific papers are published based upon its observations. Hubble's success directly inspired the James Webb Space Telescope, launched in December 2021, and the soon to be launched Nancy Grace Roman Telescope, where Hubble sees primarily invisible the ultraviolet light. Both Webb and Roman space telescopes observe in infrared, peering further back in cosmic time than ever before. Rather than replacing Hubble, Webb and Roman extends its legacy, a testament to the power of Spitzer's vision. So that's it. Thank you very much.
Thank you very much, Daz. So that's the background to why the telescope is named after Nancy Grace Roman and what a glorious career she had. And it's a shame that she didn't live to see the telescope that bears her name be launched, but she will be forever remembered as the pioneering lady who would not give up pushing the idea of the Hubble Space Telescope. Quite a remarkable lady. Well, just a brief hello to everybody in the chat. Welcome all. Glad to see that you're all here today, and we hope you enjoy the rest of this evening. As I said, this is a special about the Nancy Grace Roman Telescope, which is launching in a few days. So we thought we'd give you the complete lowdown. So when they're talking about it in the media, because of course it will be on all the front pages, yeah, and you'll know what they're talking about. So we're going to go to Roger now. Roger's going to give us a bit of background about the telescope itself. So let's bring this up for Roger. There we are, Roger. I think you're on mute, Roger. Hello, Roger. Okay, 1 second. We appear to have lost Roger's sound. We can't hear you, Roger. You're on mute. You're definitely on mute.
Can you hear me now?
That's better.
There we go.
All right. Yay.
Right.
Right.
Let's go back
Okay.
let's go back to
Right.
your presentation then.
Okay,
sorry.
so we'll go through some of the initial building stages of this new telescope. So here we go. What we're going to be doing is basically photographing lots of different things out into the universe, and we'll get into more about that later on. So we will be going to launch in a few more days, but it was originally going to be no later than May 2027, and it was going to be a 5-year primary mission, hopefully, but it'll last over 10 years. But if there's anything to go by the previous ones of JWST and the Hubble, we might be lucky to have more enjoyment out of it. But I'll move on because we do have other people doing some of the instruments on here. It will be enabling to have a good camera on there, and it will have over a 300 megapixel camera, and we'll be covering a lot faster sky coverage than the Hubble. So on the 30th of August, we'll be launching the rocket up, and here we are in its pre-launch status of being built. And as you can see, it's a reasonable size. It does have a same size mirror as the Hubble, 2.4 meter a mirror. And as you can see here, it's gradually being hoisted and assembled in this dust-free building.
With regard to the size of the mirror, it's worth pointing out that both the Hubble and the Roman telescope are originally surplus spy satellites that were given to NASA by the military. So they didn't have to build them from scratch.
Yeah. So yeah, here you got a very clear view of the actual main mirror here being in there, and here's a nice close-up view of the mirror as well. So it's going to be a good resolver, especially when we've got no atmospheric conditions to obstruct what we're going to be having to image. So it's going to be at the Lagrange 2 point. So it's aligned for the Earth for continuous communications, and it will be keeping in a good position. So it uses minimal energy to keep itself in that area. So it should be a good point to keep. So for the first 3 months after liftoff, plus 5 hours from launch, the solar panels and sunshade will deploy. And then 2 days later, the high gain antenna and aperture cover will be released. And then we'll start to get the instruments working 1 week after, and then the imaging will start 3 weeks after that. So it should be quite an interesting 90 days of testings here. So it's all going to be commissioned slowly in the first 3 months. And hopefully we will start to get some interesting data coming back. And obviously they'll be promoting it with some Hubble-esque type images that we all love to see and go, ooh. So obviously when we do get to that Lagrange point, we will be able to get an unobstructed view, no atmospheric interference, and be able to get the definition that moves on the next chapter when we've got used to the Hubble images and the James Webb. We'll be going on to another level of demonstration of how we can achieve awesome imaging and studies of objects that we will be finding out and discovering possibly some new things that we didn't even knew existed. So we will be able to get on with the images, and I'll go on from here for other people to talk about. So we've got characteristics via so we're going to be getting on to quite a lot of technical equipment, solving imaging programs, and going through all the different types of photometry that the Nancy Grace Roman will be getting into, and be exploring more images that the Hubble has sort of hinted at. And we can start to see stuff that Hubble wasn't able to resolve as well, but obviously with the new sensors and photometry, we will be able to delve more deeply into the images that this new telescope will be able to provide. So we will be getting into lots and lots of more interesting things, rogue planets, microlensing, and finding out more planets and possibly moons of those planets as well. So it should be quite an interesting few months to get things sorted and tweaked and adjusted. And once everything will become all aligned and everyone's happy, the program can start. So it should be quite an interesting thing. So we'll be having a look for dark energy structures of 1 billion plus galaxies, thousands of supernova type 1As, and how all this is going to happen in our lifetime. Thank goodness. So once we get things going over, we'll be able to tag it all through with the James Webb Space Telescope as well. Okay, so there we go. I think that's about it for me. So it should all hopefully all tie in with the other two telescopes to give us a more basic understanding of what there is out there and what new discoveries will be found.
Okay, thank you very much, Roger. So what we're going to do now, give me 1 second, is go to Michael, and Michael's going to tell us a bit about the instruments of the spacecraft, which of course are the all-important things. So Michael, when you're ready.
Okay, I'll get there very shortly. Okay,
Mike B has got a question. Lou, perhaps you might like to take this one. Can the mirror be tested to ensure there is no Hubble-type defect, or will we only be certain once it's launched and starts to return images?
Yeah, so the Hubble defect, they were rushing. My understanding is they bypassed one of the optical tests to see if the mirror was in focus, the image was in focus for Hubble. I'm sure. I mean, a commission was formed to address this. I'm sure that they have done multiple tests for this. So yes, of course, you can only be sure once it's in space and operating. But I would be very surprised to find any kind of optical defect in.
Yeah, because there was 2 tests, wasn't there, Lou? And as you said, because they did one test which didn't detect the aberration. And then they forewent the second test, which would have shown that there was a problem.
It was a management decision, wasn't it? Not a technician decision.
So, of course, when it got up, it was a bit late once it got up into the into space. And of course, when it did its first light and the images were blurred, so yeah, they were a bit of a shock.
The big difference here is that Hubble was in low Earth orbit, and we could actually go up and mess around with it, fix it, put it in the coast bar. Yeah. We cannot get out to L2, not easily.
No.
And so.
But I see that the Roman telescope is equipped with a robotic refueling port, which the James Webb doesn't have. So theoretically, if we can get out to L2 with a robot, it can be refueled to prolong its life. So that's interesting. There were lots of people who said that James Webb should have included that. but they didn't in the end. Perhaps it was a cost thing. I don't know. But
You know,
anyway,
we've never sent astronauts to L2. That would be interesting.
that's right. Although presumably it could be done robotically, what with today's level of technology. So we'll have to wait and see. That would be fantastic if they could, I don't know, double its life by refueling it when it has run out of fuel. Question from Derek as well. Would Hubble perform better in these locations?
Good question.
The answer is possibly yes, but it wasn't designed to.
No.
Because I mean, at one stage we are going to lose Hubble. I mean, just like we have, unfortunately, we've lost Swift. We mentioned a week or two ago about the mission to try and save Swift, but unfortunately that's failed. But yeah, Hubble, eventually it, because there was talk about boosting Hubble up into a higher orbit again. And I think SpaceX would offer to design something, but it was rejected. But Hubble's still working fine. Well, I say fine. I mean, it's basically baler twine and chewing gum that's keeping it going, because I think it's down to one gyro, and it's having to use other forms of actually to moving itself around.
Yeah, considering that most of its reaction wheels have failed, they've done a really good job keeping it in a stable position and able to point it. They've done an incredible job. Deep Burrito says, let's move Hubble to a moon orbit. That's a good idea.
Yeah.
But I don't think there's much enthusiasm for that, unfortunately.
No.
So there we are. Okay, Mark, over to you.
Okay. Coming through now. Right.
Okay.
This is about a couple of the instruments on the Roman telescope, but mainly about the wide field instrument, but I will touch on the coronagraph as well, briefly. Okay. So, okay, this is the wide field instrument. As Roger said, it's got the 300 megapixel camera, infrared imaging at unprecedented scale, 100 times the view of Hubble's resolution, with the field of view 200 times larger. And it's got infrared eyes to see through dust and reveal hidden galaxies. This is a photograph of how the detectors on the camera work. These are the CCDs on the camera. So there's 18 detectors of 4096 times 4096 pixels with 10 micron pixels. Those are big, detectors. Okay, so to put that in perspective, this is a example of the field of view that the Roman telescope will be looking at. This is based on a ground-based image from another telescope, but the white line outline of the main image is what the Roman telescope will see. In the small square in the middle, that is what the field of view of the Hubble can see. So you can see it's a much larger field of view with the Raman telescope than the Hubble. Put it into perspective again. Another way of looking at it. This is a photograph of an Andromeda galaxy, and the Roman field of view is overlaid there at the same scale as the Andromeda galaxy would appear. And as you can see on the top left of the Roman field of view, you've got a yellow square denoting what the Hubble field of view would be. And of course, to the bottom right, we've got the moon at the same scale as it would appear in the sky.
Wow, that's a lot of sky.
Yeah, the telescope will be equipped with slitless I can't say it either.
What is it with that word? It's an infection.
Spectroscopy.
That's the one.
Yeah, that's the one. Which removes a physical slit from the optical path using a grism or prism. I'm not going to go into detail of this, but it will be using two kinds of prism to get to the different wavelengths and the field of view for the different spectroscopy. I've got it there. Okay. So the grism will be collecting high detail spectra. The grism is a grating prism plus prism hybrid, and that will have a resolving power sharp enough to identify individual spectral lines. The target range for this grism is to target emission line galaxies, or ELGs. And the prism, which is the wide field version, wide fields of view spectra, it's a simple glass wedge, lower resolution, that sweeps across a broader range of objects in one shot. Resolving power of resolving for breadth rather than depth, a wavelength range of 600 to 800 nanometers, the widest sweep of any wide field imaging mode. For the telescope. The telescope is also fitted with an element wheel with 8 different filters isolating different specific wavelengths of light to be directed to the detector. Now, also on the telescope, we have another instrument called the coronagraph instruments. And we've got I believe we've got another video to go through in a bit to show how that works. And that's it.
Thank you, Michael. Thank you very much indeed. So that's a bit about the instruments on the telescope. And if you have any questions about any of this, by the way, viewers, don't hesitate to ask your questions in the chat. That's what we're here for. Anything at all that we might be able to help you with, don't hesitate to put them in the chat, and we'll do our very best to answer your questions. Okay, so the most important thing, obviously, is the science that the Roman Space Telescope will be doing. What exactly are its objectives in terms of astrophysics? So we're going to be looking at that after we've got two things, actually. After we've had a word from our sponsor, and then afterwards, we're going to go to the night sky and gallery for this week, just to give you guys a break and to stop bombarding you with information for a bit. So first of all, obviously, a word from... This video is sponsored by Picastro. It's like Instagram for space nerds. And as always, many thanks to Tom McCrory for sponsoring Space Oddities. So we go to Roger now for the inevitable night sky and gallery. So over to you, Roger.
Right. Okay, here we go for the last week of August already. Oh, there we are. I know. There we go. Next Tuesday is the 1st of September. Oh.
My God.
I know.
I know.
It's a bank holiday, the last one before Christmas.
Oh no!
Should have said that. Right, so we're leading up to a full moon during the Thursday-Friday period, which is also when we've got a almost complete but partial lunar eclipse. And thank Thank heavens we've got normal weather back coming this week, so it's very unlikely that anybody will be able to see it from the UK, because we'll be having thunderstorms and everything else that's overdue. So
Or the east
there is
coast of the U.S.
so we shall see. But as you can see from the skies here, looking overhead, we've got the summer triangle. We've got Cygnus, Lyra, and Aquila all there, the summer triangle, with the square Pegasus and Andromeda Galaxy coming up quite nicely into view. But we've also got Saturn coming up nicely now, so things are starting to look a little bit more interesting again after having the planets of Jupiter and Venus in the evening sky to entertain us. So there we go. But before sunset, we do have Jupiter leading the way before the Sun, and as you can see, Mercury is very close to the Sun from our perspective. So we will be getting it as an evening object at some point, but not quite just yet. And also at about the same latitude, we do have Venus there. So if you're lucky with a level horizon, you might just about capture it, although it is still reasonably close. But during the nights, we do get Saturn to come up quite nicely, and a few hours later, we do get Mars coming up through Gemini. So the winter constellations are keeping Mars company.
Yeah,
so that's.
I noticed Orion rising a couple of mornings ago when I woke up. A lovely view.
Yes. So we've just got the last few days there. We've got Pluto opposition coming up soon. So poor little Pluto. So we still get mentioned in dispatches. So there we go. It's at a poor little 14.4 magnitude, and it is still 5.95 billion kilometers away. So it is in Capricornus at the moment. So if you want to try and see it, have a look. We do have as the Americans call the sturgeon moon this Thursday, and we've also got the 96% lunar eclipse.
Whoa.
So it should be quite an interesting event. Should there be a miracle with the weather, but things are not looking very, very fortunate for us. Although we do have opportunities across, as you can see from this map, through the whole of South America, Central America, and 2/3 of the US to be able to get to see some of it at some point. So that would be good. So at UTC time over in the UK, we do get the greatest amount of the eclipse, roughly about 4:15 in the morning, with it starting about 2:20 and it will just about be setting before it finishes its proper phase of the end of the eclipse. So there we go. So there might be an opportunity at some point to see some part of it if you're lucky. If not the end, if the clouds will allow us. So what we're getting today on the sun, we've got a few little sunspots. Nothing too outrageous there, all fairly small. Not too much activity. Not too much on the way of prominence activity, but as you can see on the right-hand side, we do have a few large coronal holes there that have lined up with the Earth. So we'll see how that fares out with any activity. But I'll leave that spoiler to Daz if he's got any updates for that.
Yeah, well, actually, just before we came on air, there was an alert that I don't know, with sometime today, I think it was, that there was an M6.7 flare
Oh, right.
been released. So maybe the end of the week we may get some interesting skies, but only time will tell.
Okay. Right. Onwards and outwards and outwards to the gallery. Not as much as last week, but then not every week we get a solar eclipse. So we're back to our normal views of the night sky, which is no bad thing at all. So our first image is of the Western Belle and Witch's Broom from Jerry DeLay, which he's managed to collect and processed in PixInsight and Photoshop. Clouds nearest my nearest village. Right, okay. So this is a rather superb image here.
That is gorgeous.
Oh yeah, that is.
Very well done.
That's proper.
Proper
Yeah.
job.
Proper job. Yeah.
Yes. Try getting that with the new C-Star S50 Pro.
Challenge accepted.
Yes. And we've got a lunar image from Michael here, who captured it with his Z7 and his 500 mirror. He obviously hasn't taken it apart yet from the eclipse from last week.
That's true. That's true.
And there we go.
There you go.
And,
I'll take the solar filter off though.
Yeah, that will make a big difference, Michael.
Yeah, exactly. And I like the way the terminator is right by the edge of the large crater on the other side of the Mary Imbrium is this? And Sinus Iridium's showing up nicely there. Yeah.
Very well done. Nice lad. Well done.
Yep.
And we've got a picture from Michael of the sun, which was done last Monday, which he has kindly numbered up.
Oh wow!
So,
that's very clear, isn't it? Look at that.
Yeah.
Very nice.
It's always interesting to see how they morph as they cross the surface there. How they spread apart and get back together again, and other ones appear. So it's all very fascinating.
One thing I have noticed, and I've noticed it over the last couple of weeks, we're beginning to get. You can't see me cursor, so it's no good me circling it. But if you look at 4, 5, 16, and there's also one down towards sort of like the 7 o'clock area, that the sunspots are beginning to move a bit higher latitudes and lower latitudes again.
Right.
Well, in the southern atmosphere, which is usually a sign that we're all maybe beginning of, because it sometimes happens that the next cycle, which would be 26, could be beginning to start and influence. We still haven't finished 25 yet, which is why you've got the main ones in the equatorial areas.
All right.
Can you tell where the equator is in this picture?
Well, yes, across the middle.
Silly me.
Oh, you mean could this be tilted?
Well,
yeah, I think it might be more of a from a sort of a 7 o'clock to a 2 o'clock position.
Yeah, I see what you're on about now. Yeah, that could well be it. But maybe
that
that's what I've been.
Sense,
that's
right?
what I've seen. Yeah.
Yeah, that will make sense. Yeah.
Yeah.
Okay.
Anyway.
Yeah. There you go.
So that's what we have for this week in the little gallery. But there will be more pictures next week.
Well, we hope there'll be more pictures next week. But
absolutely.
We
I've got quite a few to send in.
Yep, we rely on you, the viewers, to send your images in. If you would like to do so, then please do. All you have to do, attach your image, one image per email, please, to an email, and send it in to gallery@spaceoddities.space, and your image will appear here on Tuesday, and you also will be blessed with your own gallery on the Space Oddities website, which, if you don't know by now, is https://spaceoddities.space. Very simple. And we look forward to receiving your images because we love looking at them.
Yes.
And so, anything you want to share with us and the other viewers, then please send them in. We'd love
any of the lunar eclipse, if you catch them, please send them in, because it looks unlikely that we'll be able to catch anything. We'll see.
Yeah.
Well, I've just had a look at our weather forecast, and it looks clear for the lunar eclipse.
Well, there you go, Andy. No excuse. Get your camera out.
It's up to you now.
Well, the question then is, will I be getting up that early? And
Yes, you
That's
will.
always a
yes,
question.
I will. Yes,
Well,
okay.
it won't be as early if it was for us, remember,
No.
because you're an hour in front. So,
But to be honest, I don't care about you. So I'm really interested in my sleep, not yours.
Truth's coming out now.
well, some of us need it more than others.
Roger, you talked about the summer triangle there.
Yes.
And I don't know whether anybody else has this experience, but when I look up at Cygnus, it always seems to be moving across the sky. I think I'm suffering from motion sickness. So, yeah.
Right.
Anyway, moving on.
Okay.
Okay. Well, what we can do now is go back to the Nancy Grace Roman Space Telescope, because, of course, what everybody wants to know, hopefully, is what is the science all about with the Nancy Grace Roman Telescope. So I'm going to be talking you through what the science objectives are for the Nancy Grace Roman Telescope and how it will really differ from other space telescopes. So we got some big questions to answer in astronomy. Questions like, what is the universe made of? How did it evolve? Well, the Roman is a next generation telescope. It's designed to investigate these sort of really deeply unresolved questions and mysteries in astrophysics, such as the nature of dark energy, the distribution of dark matter, the behavior of gravity at cosmic scales, and the true abundance of worlds beyond our solar system. Because up till now, of course, although it's a fantastic number, we've, inverted commas, only discovered just over 6,000 planets orbiting other stars. It's reckoned that during its lifetime, the Nancy Grace Roman will increase that to about 100,000 exoplanets. And this is exciting news. And the Roman may be able to image some of those planets directly. But let's talk about the actual science and why the Roman telescope is different. It does have a big survey advantage. It delivers Hubble-class angular resolution, preserved across the wide field, and as we've seen, it is an extremely wide field, 100 times wider than Hubble's field of vision, and it can observe millions of objects simultaneously, not just one at a time. So it's a true survey telescope in the same way that the Vera Rubin telescope in Chile, which, as you know, about a month ago or so, started its 10-year survey of the southern hemisphere sky, another survey telescope. So the technology now enables us to build these incredibly wide field survey telescopes, and hence to investigate a lot of questions that we have about the universe. For example, in the late 1990s, astronomers discovered that the expansion of the universe is not slowing down as expected, it's speeding up, which you probably know by now. We've given the label dark energy to that. It's got nothing to do with dark. Dark in this context simply means unknown. It's just a placeholder name for whatever's driving this acceleration. It may be a property of space itself. It may be a new type of energy field, or something stranger still that, you know, at the moment is beyond our comprehension. But the answer is we just, as Patrick Moore would say, we simply do not know. So this is one of the main objectives of the Roman telescope, to investigate dark energy. What we know about it is that it constitutes roughly 68% of the total energy content of the universe, but its makeup, actually what it isn't, let's be honest, entirely unknown at the moment. There are some ideas as to what dark energy might be. There are also other ideas that say that we've got things wrong and we don't need to invent something like dark energy, that it can be explained in other ways. Well, hopefully the Roman will sort out which of those is true. What's it going to do? It's going to measure the expansion history of the universe and the growth of cosmic structure with unprecedented precision, constraining, although not necessarily identifying the nature of dark energy. That's a very, very important point. The Roman may well not enable us to identify exactly what dark energy is, but it will constrain some of the theories and hence get us closer to knowing what dark energy actually is. The Romans also are going to investigate cosmic expansion. Now, it's going to use 3 independent techniques for this, and the first of these are type 1 supernovae, which have long been used as, if you like, standard candles in the universe, because we can measure their brightness, and all type 1a supernovae have the same intrinsic brightness, therefore we can work out how far away they are. So this is part of the cosmic ladder that enables us to measure these distances across the universe. The next technique is to observe what are called baryonic acoustic oscillations. Now, in the very, very early universe, the universe was permeated, we think, by what were essentially sound waves. And what this did for the universe, it dictated the distance between galaxies. So by measuring the distances, we can come up with an idea about how the universe has expanded over time, which will help us again with dark energy. And the third technique is called weak gravitational lensing, and we'll talk about that in a bit more detail. But these 3 distinct observational approaches, their power lies not in any single method, but in the independence. If all 3 of these types of observations agree, we've got good confidence that the result is high. If they disagree in any way with each other, something new may be at work. So each technique carries its own systematic uncertainties. Cross-checking against all 3 is Roman strategy for reaching cosmological conclusions that are genuinely robust. Romans also, a part of this, going to look at the growth of cosmic structure. Now, we think we have a pretty good idea of how structure in the universe evolved over time, right from its origins, because the early universe, of course, was remarkably smooth. There were tiny density fluctuations, just one part in maybe 100,000. Gravity amplified those fluctuations over the 13.8 billion years of the history of the universe, and it's produced the web of filaments, voids, and galaxy clusters we see today, because the universe is really based on a structure, a superstructure of these webs and filaments, which is known collectively as the cosmic web. So this is another area of investigation for the Roman. And this came about because, first of all, dark matter provided the gravitational scaffolding for structure to form. Dark energy works against gravity, slowing the growth of structure over time. So Roman will trace galaxies, clusters, and lensing across cosmic history, constraining both components simultaneously. The Roman will also map dark matter, because, as we know, dark matter does not emit, absorb, or reflect light. It can't be seen directly, but its gravity bends and distorts the images of more distant galaxies, an effect called gravitational lensing. And you can see in this image here those arcs, which are the magnified images of distant objects whose light has been bent, if you like, by foreground objects. When this distortion is subtle and statistical rather than dramatic, it's called weak gravitational lensing. By measuring the coherent alignment of millions of these faint background galaxy shapes, Roman can statistically reconstruct the distribution of invisible mass across enormous areas of sky. Now, Roman, of course, will not image dark matter directly. It infers its presence from the way it warps the light of galaxies behind it. And this is absolutely a beautiful image here of all those arcs, which are the magnified images of distant objects, as I said, whose light has been bent by foreground objects and magnified. This will enable the Roman as well to test general relativity, because general relativity makes precise testable predictions about how the universe should expand and how structure should grow. And of course, those two predictions are linked. So the Roman will measure the expansion to measure how fast the universe is growing over time. It will measure the growth of structure in the universe. How fast do galaxy clusters and filaments assemble? And compare that to general relativity. Do the two agree? Now, if they don't, if Roman's observations don't agree with general relativity, this would signal, you'll never guess, modified gravity, the MOND that we've talked about on Space Oddities a lot, that our understanding of gravity is either wrong or needs slightly tweaking. So this is a hypothesis to test. It's not an established fact. But if Roman's observations agree with GR, then that sort of puts another nail in the coffin of modified gravity, or modified Newtonian dynamics, as it's known, MOND. And it may not be dead, but it's certainly a bit ill.
I got £5 on the table right here for you, Andy.
Okay, well, let's up that. Put 10 quid. I bet
You're on.
I bet you 10 quid that Roman's observations agree perfectly with GR. Bet you anything.
Done.
Okay, right, that's a bet.
Whatever a quid is, but done.
Please bet responsibly.
Yeah.
Yes. Don't
Other
like
options
us.
are available. Okay, now interestingly, the Roman is also going to carry out this census of exoplanets. And this uses gravitational microlensing, where a foreground star and any orbiting planets passes in front of a more distant background star. The foreground mass briefly focuses and brightens the background star's light in the same way that it does with distant galaxies, as we saw with those beautiful lensed arcs. So this technique reaches planets that transit and radial velocity surveys cannot easily find. Now let's just remind you what those two terms mean. Transit is where a planet passes in front of its star, briefly dimming the star's light by perhaps 1%. But of course, we have instruments sensitive enough to detect that dimming. The radial velocity is where the gravity of a planet pulls on the star, and the star moves alternatively towards us and away from us. That's known as the radial velocity survey. And those types of surveys cannot easily find planets that are some distance from their host stars, because if you have a planet that's a really long distance from its host star, its year is going to be a very long time indeed. So if you want to see it passing in front of its star, you have to wait a long time. Also, of course, don't forget that we may be missing a lot of planets because their orbits are at 90 degrees to us from our perspective, so they never pass in front of the star. So it'd be interesting to see how this exoplanet census turns out. The radial velocity method also cannot show us low mass planets because their gravity isn't strong enough to pull on the star, so that the coming and going, if you like, of the star towards us and away from us can be measured because it's too little. And we've also got a problem with planetary systems that are thousands of light years away in the galactic disk, which, as we know, is a very crowded place. So finding these planets up till now has been difficult. We've also got these weird planets that float through the galaxy, not bound to any star. How do they get like that? Well, the best bet is that in the past, when they did orbit a star, there were interactions between massive planets, which effectively kicked planets out of their star systems, and then they're doomed to roam the galaxy forever. So the Roman solves a lot of these problems. And here's just a little bit more about that. So if you look at the graphic on the left, and I hope you can read that. So we've got the transit surveys are great for covering close-in planets, close into their stars of moderate to high mass. Radial velocity, again, covers close-in planets that are massive, whose pull on their star can be measured. And then we've got microlensing, which allows us to look at stars at wide orbits and lower masses. So this microlensing survey will fill this gap statistically, enabling the first generally unbiased census of planetary system architectures across the galaxy. And it's fascinating because if the Romans are going to find up to 100,000 exoplanets, it will enable us to see more and more how special and different our own solar system is, because no solar system that we found so far has been anything like our own solar system. And it's going to be really interesting with 100,000 discoveries of exoplanets, you can do some really good statistical analysis and perhaps come up with a sort of a categorization of star systems that we haven't been able to do before. So this is all exciting stuff. So Roman will ask, how common are planetary systems like our own, and how common are those unlike it? So for the first time, we'll be able to come up with some statistical information about the categorization of star systems. Now, I've just got a short video here about gravitational microlensing, showing you how it works. So you have a planet and a star passing in front of a more distant star. And as it does so, you see the light curve rise and then fall as the star moves away from it. And then you get the same thing with the planet. And this generates this characteristic double peak. And this is what's known as gravitational microlensing that we'll be able to detect. Now, we mentioned the coronagraph, which we'll come back to in a moment. But with a coronagraph, which effectively blocks out the light of the star so that you can see what the hell is going on, then you get lovely sequences of images like this. This is the star system HR 799, and that circle in the middle with the star in it is the coronagraph. It's blocking out 90+% of the light from the star, enabling us to see the planets. So this isn't a representation. These are actual images of planets in the HR 8799 system. And let's tell you a little bit more about the coronagraph. So just give me 1 second, and we will have a look at this short video that will tell you about the coronagraph in a bit more detail.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. WFIRST doesn't block the star's light with an opaque disk as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear, while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects the distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into
Every discovery begins.
Well, 1 second. Okay, so we're now going to look at these free-floating worlds, these planets without stars. And we don't know how many of these there are. They're not reckoned to be that common, but we've discovered a few already. So the way that this will work out, the signal from these planets is a very brief symmetric brightening of a background star lasting hours to days, as we saw in the animation, where there's no star detected that the planet is orbiting. Now, the challenge is extremely short timescales because these observations will be over in a flash, and rare alignments require monitoring millions of stars continuously to make sure you don't miss anything, exactly what the wide field of the Roman telescope enables. But the payoff is a statistical census of free-floating planetary mass objects. And this would constrain models of how planetary systems form, migrate, and disrupt. Now, looking at Roman as a discovery machine, then it's all about discovery. This is all totally new stuff to us, the capabilities of which we've never had before. And it will generate data sets of extraordinary scientific breadth, far beyond their primary dark energy and exoplanet goals. So we're after the statistical information, which you would expect from any survey. And what we need to answer is, how do galaxies assemble, quench, and transform across cosmic time? With quasars and active galactic nuclei, AGNs, which are supermassive black holes in the act of growth across a range of redshifts, that will also be part of the Roman study. Supernovae, kilonovae, and other brief phenomena caught in real time by the Roman telescope. The structure of the Milky Way, stellar populations, star streams, and the galactic disk will be resolved in depth. And of course, the most exciting thing to come out of any new telescope that we always look forward to is that the most significant discoveries may be ones nobody has yet anticipated, because we don't know what we don't know. So to sum up then, the big questions from Roman: what drives cosmic acceleration? How is dark matter distributed? Does gravity obey general relativity at cosmic scales? How did cosmic structure form? How common are planetary systems? And how many worlds drift beyond our current surveys? How are we going to discover them, and what will we discover? But the fact that for the first time, we'll be able to come up with some really good statistical analysis of the exoplanets and star systems is going to be absolutely fantastic. So we all look forward to that. So there you are. Those are the science goals of the Roman telescope. Lou, did you want to say anything?
You know, it's interesting. I've seen this with Hubble, and I've seen it with James Webb. These are primarily, intentionally, astrophysics instruments, right? Galaxies, star clusters, dark matter, dark energy, all of this, great. But they all have solar system science objectives, and so does Nancy Roman.
Yeah,
just our own little solar system. So Roman is it's a wide field survey instrument. It's a very sensitive infrared optical system and detector. And so this is going to make it fantastic for planetary science and solar system discovery. So for example, I would expect Roman to identify many as yet uncatalogued dwarf planets and even distant moons in the outer solar system. I would expect discovery of hundreds, maybe thousands of TNOs, of trans-Neptunian objects. And it may be effective in gathering population statistics of small bodies. When we say small bodies, we mean asteroids, comets, that kind of thing. And because these are the remnants of the formation of the solar system, they tell a story about how the solar system is constructed. And so from these observations, we could potentially reconstruct the collisional and the migration history of the outer solar system, which has an impact on the formation of the inner solar system, the Earth. So, certainly there's real value in exploring our own solar system.
Yeah, indeed. So it's going to be a fantastic new age of science. We've got the same well, I've got the same anticipation that we had with the James Webb Telescope entering a completely new era of astronomical study, and who knows what the results will be. We may get some. Hopefully, we'll get some big surprises in the same way that the Webb has given us some really puzzling questions about the very early universe. So fantastic. Well, what we're going to do now is to go over to Daz, because Daz is going to tell us about the data. What happens with the data? How is the data processed? Who ends up with the data? How does it get there? So Daz, over to you.
Right, just bear with me. I want to share all of this. Right, okay then. So basically, of course, we're going to have all of this information, all this data is going to be coming in from the Nancy Grace Roman, but it's got to be managed and it's got to be sorted. So basically, the Nancy Grace Roman Space Telescope, it's a next generation observatory set to transform our understanding of the cosmos through unprecedented wide field surveys, which you've all been hearing about, and an advanced data pipeline and an open access data strategy built for the entire scientific community, which is good to hear. Launching in the mid-2020s, well, we know hopefully that's going to be in the next few weeks. Roman is designed to answer some of astrophysics' most profound questions, as we've already heard, mapping dark energy, tracing galaxy evolution, and discovering exoplanets at scale. Maps vast sky regions simultaneously, observing thousands of galaxies in a single exposure. As Michael explained, the view is going to be so wide that it's going to encapsulate so many galaxies. It's going to be absolutely, I'm going to use the word, sorry the pun, astronomical. High resolution imaging reveals the early universe structure and galaxy evolution over cosmic time. So we'll be seeing lots more of these little red dots, as we call them, which there's debate about what they actually are, still ongoing. We will be it detects and characterizes distant exoplanets by measuring gravitational lensing events. Well, we've just spoken about that. The data pipeline from photons to science. Roman's observational program is structured around two complementary approaches, maximizing both breadth and scientific precision. The legacy survey produces expansive community-ready data sets covering enormous swathes of the sky. The foundation for thousands of independent research programs, and it's targeted observations, and it's got dedicated pointings for specific scientific objects, time domain events, which is another big thing we'll be looking at, and transient phenomena and precision cosmology measurements. Roman's pipeline is engineered to handle data volumes far exceeding previous space missions, with rigorous calibration and reduction at every stage to ensure publication quality outputs from day one. Each stage is automated and scalable, ensuring researchers receive timely, high-fidelity data products from raw exposures through to fully reduced catalogs ready for science analysis. Why scalability matters. Roman's wide field detector would generate data volumes that dwarfs previous infrared missions. The pipeline's architecture is designed from the outset to scale horizontally, processing multiple concurrent data streams without degradation in quality or latency. Parallel processing across distributed compute nodes, automated quality control at each pipeline stage, and timely data releases to support fast cadence science. Before Roman opens its eyes, the community needs to be ready. The data challenge is a structured, innovative, providing researchers with realistic synthetic data sets to develop, test, and validate their analysis pipelines in advance of first light. Participants receive simulated observations mimicking Roman's wide field surveys, including galaxies, stars, and exoplanet microlensing events under realistic noise conditions. Teams develop the benchmark methods for calibration, source extraction, and photometry, building the analytic toolkit needed for real Roman data. The challenge fosters cross-disciplinary engagement, enabling researchers to share approaches, identifying common obstacles, and converge on community-validated solutions. Roman's data will be released under an open access model, available to researchers, educators, and the broader public without restriction, which is always good. The archive will include raw frames, processed data products, observational metadata, and analysis tools. Data will be released in staged trenches, enabling immediate science from day one, whilst the full archive builds across the mission's lifetime. Roman represents a landmark in survey astronomy, and preparation starts now. There you go.
Fantastic. Thank you, Daz.
Brief and to the point.
Absolutely. So yes, I mean, it's often said that the big change over astronomy over the last decade or so is that these telescopes, these instruments, are basically data machines pumping out huge quantities of data. For example, when the square kilometer array comes online towards the end of this decade, the world's biggest radio telescope split between Australia and South Africa, that's going to be processing at any one moment more data than the entire internet. So, these systems have to be designed, the pipelines have to be designed. We couldn't have done it a few years ago because the computers just didn't exist to handle that amount of information and process it quickly. So as the whole computing sphere has evolved, so have the instruments that pump data into the networks. And of course, all that information, as Daz said, will be publicly available. You'll be able to look at the data. And I'm sure that there will be some citizen science projects, particularly on the Zooniverse, associated with analyzing the Roman data. Incidentally, there are already several projects that you can get involved with at the Zooniverse to analyze the Vera Rubin data. And if you want to actually have a look at the Rubin data yourself, then what you need to do is to sign up with one of the data brokers. It's all totally free, of course, because the information is freely available. And basically, the data brokers is the software that routes the finished data products to whoever is interested in looking at them. So basically, you'll be able to you're able to go to a data broker, filter the information, because trust me, you don't want all the information from the Rubin telescope. So if you're interested in supernovae, for example, the observations the Rubin is made of supernovae, you'll be able to filter the data for that and get all the Rubin images. So
couple of thoughts.
Sorry.
A couple of thoughts, if I may. First of all, in terms of the volume of data, there's a relatively new technique called chunking, which allows you to grab not something less than a file or something less than a data set, and reduces the input output ingress egress time and cost for accessing data. But the Roman data and the ground-based data and Hubble and James Webb all archived, this represents a treasure trove in correlative science and archival research that is going to be spearhead, because a lot of it, some of it's spectral, and that's great. A lot of it is looking for patterns in the images, and so this will be, I anticipate this will be driven largely by AI agents that will be very
Yeah.
efficient at looking for pattern recognition.
Yes, indeed, indeed. You know, AI is proving a fantastic tool for astronomers to do simply that: analyze enormous sets of data that it would take humans a long time to do, and computers without AI a long time to do. So you can expect much more integration of AI into astronomy moving forward, because a lot of people, the only evidence they ever see of AI are silly pictures of cats and other nonsense on social media and silly videos. But don't forget, AI is revolutionizing science. And a good example of this is the fact that AI recently came up with models of how 2 million proteins fold, which is reckoned to be about the maximum number of proteins that there could possibly be. And in decades and decades of research, humans have only managed to work out the protein folding of a few hundred proteins. And in just a few hours, AI worked out the rest, up to 2 million. So AI is revolutionizing science, and it's just continue to get better and better. Okay, so where do we go from there? Well, Daz is now going to tell us about collaborations between the telescopes that we've been talking about. So back to you, Daz.
Okay, just bear with me a second. Right, okay then. Well, of course, all this information, it's all well and good with the Roman doing its own thing and doing its own data. But basically, it's going to perform massive collaborations. And basically, it's being seen as NASA, the NASA's Nancy Grace Roman Space Telescope is the 5th, as they call it, flagship observatory, and joins forces with Euclid, the JWST, James Webb Space Telescope, Hubble, and Rubin. And it's going to collaborate with all of these observatories to unlock the deepest mysteries of the cosmos. Let me just get rid of that. Okay. Formerly NASA's W1st, the Nancy Grace Roman Space Telescope features a 2.4 meter primary mirror and a field of view 100 times wider than Hubble's, and we've spoken about that, enabling sweeping sky surveys impossible for any prior space observatory. It operates primarily in the infrared, near infrared, bridging the gap between Hubble's optical and JWST's infrared reach. Right, no single telescope can answer all of cosmology's grand questions. Roman is designed to work in concert with the world's most powerful observatories, combining wide field surveys, infrared precision, and time domain monitoring into the unified scientific program. Roman and JWST are built to be complementary. Roman conducts sweeping wide field surveys, producing vast catalogues of distant galaxies, gravitational lenses, and exoplanet candidates. JWST then targets the most scientific compelling objects for high-resolution spectroscopy and detailed physical characterization. This division of labor is not merely logistical, it is scientifically strategic. Roman's breadth eliminates selection bias. JWST's depth provides the physical interpretation. Together, they address questions ranging from how the first galaxies ignited to whether distant worlds could harbor life. Roman and Rubin. They're again a complementary design. Neither mission can achieve its full scientific potential. The Vera C. Rubin, the Vera C. Rubin Observatory's Legacy Survey of Space and Time, bit of a mouthful, LSST, will photograph the entire southern sky every few nights, cataloging billions of transient events. Transients events. Roman space-based infrared surveys and Rubin's ground-based optical cadence are naturally complementary, cross-validating measurements of supernova and standard candles, refining cosmic expansion histories and producing more robust models of dark energy dynamics. Where Roman maps the large-scale distribution of galaxies across the cosmic time, Rubin captures with precision the flickering, explosive, and variable foreground. So we're talking about supernova type A, type 1A, variable stars and asteroids. Rubin will monitor the transient events. Roman provides infrared counterparts and parallaxes. Cross-validation, independent data sets reduce systematic errors in dark energy measurements. Together, they assemble a four-dimensional picture of the universe, its spatial structure, and its temporal evolution. This synergy is expected to place some of the tightest constraints yet on the equation of the state of dark energy. Won't advance. Why won't it advance? Excuse me. Let's try this. The Roman-Euclid partnership targets the two most puzzling puzzles in modern cosmology: dark energy and dark matter. Roman's exceptional wide-field imaging generates extensive galaxy catalogues with precise photometric redshifts, while Euclid contributes sub-percent level measurements of galaxy shapes. The key observable for weak gravitational lensing, the most powerful probe of the dark matter distribution. Hubble's 3 decades of deep field imaging, from the Hubble's deep field to the extreme deep field, established the benchmark against which all galaxy surveys are measured. Roman's 100 times wider field of view allows it to replicate and dramatically extend Hubble quality imaging across areas of sky previously impractical to survey. Hubble Space Telescope's ultraviolet coverage also fills a wavelength gap Roman does not address, making joint analysis essential for studying stellar populations, stellar formation rates, and interstellar medium across cosmic time. The Roman Space Telescope does not operate in isolation. It is the connective tissue of a new era of collaborative astrophysics. By combining Roman's wide-field infrared surveys with the complementary strengths of the JWST, Euclid, Hubble, and Rubin, the scientific community will achieve an unprecedented multi-wavelength, multi-messenger view of the cosmos. So that is the 5 flagship observatories. There you go.
Thank you very much, Daz. So yeah, very much a collaborative effort with other instruments, synthesizing a huge pool of data. And hopefully, over the next few years, we will get lots of answers to the questions that Roman is there to ask. The dark universe, exoplanets, everything we've talked about. Well, that brings us to the end of our look at the Nancy Grace Roman Space Telescope. And in case you're wondering how you can watch the launch, we will be covering the launch live on Sunday. And we're going to go live at 12 o'clock UK time, 12 midday UK time. We'll be going live. The launch is scheduled for 12:26, if I remember correctly. And we hope you can join us on Sunday just to watch the Roman Space Telescope finally take to the skies and set off on its long journey to L2. But I don't know how much of that coverage they're going to show. But anyway, join us for the launch. We'll talk you through it and answer any questions you have. And we look forward to seeing you if you have absolutely nothing better to do on Sunday. So join us at midday on Sunday here on Space Oddities for the launch of the Nancy Grace Roman Telescope. I'd like to thank Lou and Daz and Roger and Michael for their contributions. And guys, I think we have time to squeeze in a constellation of the week. So whose turn is it this week, I wonder?
Silence.
Crickets.
They don't want to do it. No, you're
Is that
both on mute, so we won't get an answer from either of them. So okay.
I don't think it was me.
Roger's on
Oh,
mute as well.
oh,
Well, what
wow.
I've got one thing that I saw this week, which I thought was fascinating, is reference to the sun.
Oh yes.
If we can just pop that up, that'll be great. Let me just see if I can find it.
This was amazing.
Absolutely amazing. Right. Share. Right. What we have here is a picture of the sun. Now, let me just start this GIF. Now, let me just see. I've lost, because it's all white, I've lost my presenter view. There we go. So what we've got here is just start this and let this play. Right. What we've got here is the sharpest images ever taken of the sun's surface, revealing ribbons of solar plasma curling into tight wave-like vortices near the edge of a sunspot. The pattern never before seen on our star. The experiment behind this discovery was designed to push the technical limits of a new camera system, not hunt for any solar phenomenon. But the vortices it captured turned out to be the signature of a well-known fluid dynamics phenomenon called the Kelvin-Helmholtz instability. Sorry?
That old chestnut.
Yeah, old chestnut. Yeah. They dragged it out again. The first confirmed sighting of this process on the sun. The serendipitous discovery may also help answer one of the solar physics' longest standing mysteries: why the sun's outer atmosphere runs hotter than the surface below it. We didn't intend to. Thomas Rimmel said we didn't intend to produce big science results. Certainly not big science results that end up on the cover of Nature with this experiment. Thomas Rimmel is a study co-author and National Science Foundation's at Daniel K. Inouye Solar Telescope in Hawaii, and he's the associate director. I mean, if you look at this, I mean, these images are totally stunning.
Amazing.
What I'll do is I'll just let it run one more time. It's to see the sun's surface in this detail is absolutely fantastic. It changes our whole thinking about how this is. I mean, we know that all this has been going on, but to actually see it, all this magnetic sort of like stuff being pulled around and these ripples, these mergings and things like that, and then to actually sort of like be able to put it to the Kelvin-Helmholtz instability is absolutely fantastic, and then to create also an image at the end of what's actually causing these things is amazing. But as I said, this is also from a ground-based telescope.
Yeah, it's
So who needs Nancy Roman?
Yeah.
So I'll just let this run to the end, and then we'll do the thing. But it's absolutely beautiful. It's stunning. Who would ever actually think we would see something like this?
I know.
So
just absolutely stunning.
I don't know if I mentioned at some earlier date, but Jim Green, who was at one point the head of planetary science at NASA headquarters, he's a big hot air balloon guy, and he's very interested in hot air balloons and how they were used in the Civil War, and he's also a planetary scientist. So he took the planetary decadal survey and he flipped through it, and he thinks he figured out that a large percentage of the planetary science objectives in the decadal survey could be accomplished with balloon-borne instruments.
Oh, really?
Cheaper. Yeah.
Wow.
right, that's fantastic.
That's just stunning.
Yeah.
Absolutely stunning. Thank you for that, Daz.
That's all right. We'll stop it there. So
Yeah, absolutely. So, the more we learn, the better the science gets. And this contribution from the telescope in Hawaii, which is it's a new telescope. It only came online, I think, about a year and a half ago. Had been under construction for some time, and this has proved its worth by delivering those.
I mean, it's done some really amazing work already. It hasn't been around that long. I mean, it won't be long before you'll be able to do it with a C-Star 50. So don't worry. So you won't have to spend out the billions of pounds to build these things.
I saw it. I saw it right here on my cell phone. It's on sale.
There you are. There you are.
I'm just saying.
Okay, so if you would like to support Space Oddities, you can, of course, buy us a coffee by scanning the QR code here or clicking the link that should have just appeared in the chat. And any contributions towards keeping our caffeine levels maintained will be gratefully appreciated. I would like to thank those of you that have donated to Space Oddities tonight with your hard-earned cash. Thank you so much. We do appreciate it. All of the money goes towards keeping us going. So, any money that you've got nothing better to do with, and, we've all got that, of course, then, you're more than welcome to buy us a coffee. You can also donate directly to Space Oddities, of course, by clicking the Super Chat icon. That's the icon with the $sign on it, directly under the chat window. That would allow you to make a direct donation. Don't forget, we still have the Space Oddities T-shirts on sale. And if you want to buy one of those, they are £20 postage, and packing, and very good quality they are too. And of course, the Space Oddities hoodies, which start at £40, including UK postage and packing. And if you're outside the UK, please add £10 to the total value of your order to cover the postage. We have been discussing today, actually, expanding our merchandise range. And if all goes well, if it all works out, we'll soon be offering you fantastic Space Oddities coffee mugs. So we shall look forward to offering those to you at a very reasonable price. We haven't decided the price yet. Everything the guys suggested as a price, I just said double it or triple it.
Yeah, I mean, you got to produce your own. You got to use your own coffee.
Yeah, you've got to use your own
coffee not supplied.
So, but we hope to bring you news of that soon, because Michael is sending off a test mug just to make sure the mugs are okay. And if that's all okay, we'll be able to add the fantastic Space Oddities coffee mugs to our range of merchandise in a little while. Not quite yet, but in a little while, hopefully in the autumn.
Yeah, Michael drew the short straw to be our mug for the test mug.
Yeah, it's funny how he always does that. Yeah. Anyway, we're going to draw things to a close here on Space Oddities for this evening. We'd like to thank you all for being here. We hope you've enjoyed tonight and learning all about the Nancy Grace Roman Telescope. Don't forget, if you can, join us on Sunday at midday here on Space Oddities for the launch of the aforementioned telescope. We're looking forward to it, and we hope you are too. And we'll be able to answer any questions you have and just basically talk you through the launch. As we said earlier, it is launching on a SpaceX Falcon Heavy, which has a 100% operational record, so we don't anticipate any problems, but one never knows, of course. So we'll look forward to seeing you on Sunday. And in the meantime, thank you for being here, as always. And if you're new here, we hope you'll come back. So from all of us at Space Oddities, have a fantastic week. Be good, look after each other. So from myself, from Daz, from Roger, from Lou, and from Michael, good evening, and we hope to see you on Sunday. But if not, we'll be back next week, 8 o'clock UK time on Tuesday, normal time. So take care, everybody, and thank